All right, the next example we have is example 2, where we are asked to calculate the total mass of a wire in the shape of a parabola y equals x squared, for which x is between 1 and 4 centimeters. And we are given the mass density of the wire. So if we're at the point x comma y on the wire, then the density of that material is y divided by x grams per centimeter. So in general, before we tackle example 2, just a quick comment on this remark right here, which essentially is saying that if you integrate, let's say, if you integrate mass density over something, then you get back the mass of that something. And this works for any density in general. It doesn't have to be mass. Like, for instance, you could have a three-dimensional region, W, and let's say we integrate the charge density or charge distribution, something like that. This would equal total charge of that region. So whenever you do a integral of a density of something, you get back that total something. So that's exactly what's going to happen here. We're given the mass density, and we want to know calculate the total mass. So ultimately what we want to do here is calculate, so the mass of our wire, let's say the wire is, we're going to call it C since the wire represents a path. This would be the integral over C of the mass density function, ds. So let's go ahead and chip away at this. Here's our xy axes. We know that the parabola y equals x squared looks like this. But because we're only doing from x equals 1 to 4, we don't need the full thing. We really just need the portion between 1 and 4. So if we go ahead and draw that, let's say right there. So this is what we're going to call our path C. It's the portion of the parabola y equals x squared for x between 1 and 4. So unlike the previous example, in this example they did not give us a parameterization, so we have to come up with a parameterization on our own, which is nice to do because if you notice that your path that's being described to you is given by a function, then you can just let t be the independent variable of this function and then let the other components depend on that variable. So for instance, let me write this in red. In general, to parameterize the graph of y equals a function of x for, let's say, x between a and b, we would let x equal t for t between the same values a and b. Therefore, or then, r of t would be given by t comma f of t for a planar graph. So that's exactly what we'll do. We're going to let r of t equal t comma t squared for t between 1 and 4. In that case, this integral over here will continue. This is the integral from 1 to 4. Our function is y over x, so this would be y over x. Again, we're getting these from our parameterization. This tells us what x and y are. And then we have to multiply now by the magnitude of the derivative. So let's go ahead and take that derivative. I'll do this over here. So r prime of t equals 1 comma 2t. So the magnitude of this is 1 plus 4t squared. You can simplify this really quickly by canceling one of those t's. And then this is a Calc 1 integral. Just let u equal 1 plus 4t squared. We can get an exact answer for this, but it's a little bit, it's perfectly fine to do, but I will go ahead and just write down for sake of quickness, being quick, the decimal. So the decimal here is 42.7, and the units on this would be grams.